In this experiment, we are going to study the clippers and clampers circuit. These circuits modify the shape of the waveform. The primary component of these circuits are diodes, capacitors, and resistors. Different combinations of these components are used to get the desired result. Clippers, as the name suggests, are used to clip out or remove a certain portion of the waveform without distorting the remaining part of the input waveform. The direction of the diode determines which portion of the wave will be clipped out. Clipper circuits mainly comprises of resistors and diodes. Transistors can also be used, but in this experiment we will focus on the clippers made using diodes. There are two kinds of clippers, series clippers and parallel clippers. In series clippers, the diode is in series with the load, but in parallel clippers, the diode is parallel to the load. Now let us understand the basic mechanism of clipping in series clippers. We can see a complete sine wave for the input voltage Vi. We know that when the diode is forward biased, it acts just like wire or a short circuit to be more precise. Let us now focus on this portion of the wave. In this part, the diode is forward biased, so diode will act just like a wire and let the entire wave pass as it is, which we can clearly see in the output. But in this region, the diode is reverse biased as the direction of the voltage is reversed, and we know that in this case the diode will act like an open circuit and will not let any current pass through it. So output voltage in this case will be 0, which we can see in the output for this region. So this circuit is clipping out the entire negative region of the waveform. In this circuit, we have assumed the diode to be ideal. Now in next example, we will consider the fact that the diode have a threshold voltage of 0.7 volt. This is a parallel clamper circuit. We can modify the threshold voltage of clipping by adding a battery. For example, let there be a battery of 1 volt. And we already know that the threshold voltage of diode is 0.7 volt. So a total of 1.7 volt is developed in this region in reverse bias for the diode. In the case of parallel clipper, when the diode is reverse biased, no current will pass through the branch in which diode is present. Entire current and hence the waveform will pass to the output. So the entire input waveform of positive part of the signal is obtained at the output. In the negative part of the signal, the diode is forward biased, but due to 1.7 volt present in the diode branch, no current will pass through this branch until negative 1.7 volt is reached by input waveform. After 1.7 volt, the entire input current will pass through the diode because it is now acting like short circuit. So the output which is being obtained for the input voltage beyond negative 1.7 volt will just be negative 1.7 volt DC voltage which is present in the branch having diode and battery. The part of the waveform beyond negative 1.7 volt is clipped off. We have discussed the theory about clipper circuits. Let us jump straight into the experiment.
Now we will see the working of different types of clipper circuits. For this purpose, we are using a software Multisim. It is a circuit simulation software developed by the National Instruments. The first is an example of a biased series negative clipper. For this we have a 15 volt VRMS supply operating at 1 kHz, a diode, a 470 ohm resistor, a 5 volt battery. All these components are connected in series with the power source. As you can see in the circuit that this diode is connected in series with this 5-volt power supply through a 470 ohm resistor. Now we connect the probe A of a CRO to the input signal and probe B of a CRO to the output signal and switch on the circuit simulation. As you can see, this is our input signal, 15 volt VRMS signal operating at a 1 kHz frequency. And this is our output signal. One can easily see in the graph that the negative part of the signal is clipped off. This is the working of a biased series negative clipper. From this you can observe the clipping action of this circuit along with the input and output waveforms. In the next part of the experiment, we will see the working of a biased series positive clipper. The construction of this circuit is similar to the previous one, that is biased series negative clipper. The only change is that in this circuit the diode is reversed. The probe A of CRO is connected to the input signal and probe B is connected to the output signal as in the previous case. Now we will switch on the circuit. We can see that this is our input signal, 15 volt VRMS operating at 1 kHz frequency. And this is our output signal. The positive part of this signal is clipped off as it is shown in the graph. This waveform is just the reverse of what we observed in the previous circuit. The positive part of the input waveform is clipped off, whereas the negative part is still there in the signal. This is the working of a biased series positive clipper. After understanding the working of series clippers, now we will move on to the working of parallel clippers. The first in this series is biased parallel positive clippers. This is the circuit schematics of a biased parallel positive clipper. As you can see in this, the output is taken parallel with the diode and the 5-volt battery. The A probe of a CRO is connected to the input signal and the B is connected to the output. Now we will switch on the circuit. As you can see, this is our input signal as in previous cases. And this is our output signal. This output signal is similar to what we observed in biased series positive clipper. The positive part of the waveform is clipped and the negative form is still there in the signal. The main difference between this and the biased series positive clipper is that in this the output is taken parallel with the diode and the 5-volt power supply, whereas the resistor is in series with the 15 volt VRMS supply and the 5 volt and the diode. After designing a biased positive parallel clipper circuit, we will now design a biased negative clipper circuit. Only we have to do is to reverse the direction of this diode D1. This is the circuit schematic of a negative parallel clipper circuit. We will now switch on the simulation and observe the output. As this is our input signal, the 15 volts VRMS with 1 kHz of frequency. This is our observed output. In this you can observe that the negative part of the waveform is clipped. This is similar to the unbiased negative clipper circuit we saw in the previous experiment. From this you can observe the working of a negative and positive parallel clipper circuits. Till now, we have seen examples of positive and negative clipper circuits. These circuits clips off either the positive part or the negative part of the waveform without affecting the remaining part. We will now design a special type of circuit which clips off the positive and the negative parts of the waveform simultaneously. For this, we have a external supply of 15 volts VRMS operating at a frequency of 1000 Hz, a 51 kilo ohm resistor, two diodes T1 and D2, two external biases 5 volts and 2.5 volts as shown in the figure. These components are connected according to the given schematic. The probe A of the CRO is connected to the input signal and the probe B is connected to the output. We will now turn on the circuit simulation and observe what waveform we are getting. As you can see, this is our input waveform, the 15 volts VRMS operating at a 1000 Hz frequency, and this is our output waveform. It can be easily observed that the positive part and the negative part of the waveform both are clipped. These circuits acts as both the positive clipper and the negative clipper because we have used two external biases, that is a bias of 5 volt and a 2.5 volt. These are special circuits designed to clip off the positive peak as well as the negative peak of the same waveform without affecting the other parts of the waveform. One speciality of these circuits is that we have used two diodes D1 and D2 in different biased conditions as shown in the figure. This is the output we get when we design such a schematic.
Now let's discuss about clampers. The clamping circuit clamps or shifts a signal to a different DC voltage level. In other words, it just shifts the waveform in positive or negative direction without affecting its shape. Clamping circuit consists of diode, capacitors and resistors. It can also employ an independent DC supply to introduce an additional shift. Positive clamper is the one which shifts the signal in positive direction, and negative clamper shifts the signal in negative direction. Let us understand the working of a clamper. Consider this circuit of a positive clamper. If Vp is the peak voltage of input AC current, during the negative half cycle the diode is forward biased, hence acts as short circuit. The capacitor gets charged to negative Vp. During the positive half cycle, the diode is reverse biased, and along with voltage Vp, the capacitor also starts discharging, which results in an output voltage of 2 Vp. Hence, the entire signal is shifted by Vp. The negative clampers follows the same mechanism. We have discussed the theory about clamper circuits. Let's jump straight into the experiment.
Now we will see the working of a clamper circuit through circuit simulations in Multisim. For this we have a 15 volt VRMS power supply operating at 1 kHz, a diode D1, a capacitor of capacitance 0.1 μF. All these components are connected as shown in the figure. The A probe of a CRO is connected to the input signal, whereas the B probe is connected to the output. We will now switch on the circuit and observe the working of this clamper circuit. As you can see, this is our input waveform, 15 volts VRMS at 1 kHz frequency. And this is our output waveform. The main difference between the two is that the output waveform is shifted upwards by this clamper circuit. There is a change in waveform due to the circuit, and this circuit clamps the waveform to a different level as shown in this figure. This is an example of a positive clamper circuit in which no external biasing is present. It clamps the output waveform upwards as we observed in the graph. Now we will observe the working of a negative clamper which shifts the waveform downward. The only difference between these two circuits is that in this the diode is in reversed condition. This is the circuit schematics of a negative clamper. We will now observe the working of the circuit. As we see, this is our input waveform, and this is our output waveform. As you can see in this diagram that the waveform is shifted downward. This is the working of a negative clamper circuit which shifts the waveform downward. The only difference between a negative clamper and positive clamper is that in this the diode was in reversed condition. In this circuit no external biasing was present. Now we will see what happens when an external biasing is present in the circuit along with the 15 volts VRMS power supply. Till now, we have seen examples of unbiased clamper circuits in which no external voltage were present. Now, we will discuss about biased clamper circuits in which there is external voltage present in the form of battery. In this circuit, we are using a battery of 5 volts as an external bias. We will now switch on the circuit and observe what we are getting as the output. As you can see, this is our input signal, the 15 volts VRMS with 1 kHz frequency. And this is our output signal. As you can see, the minimum of this waveform is not set at 0, which there was in the case of the unbiased clamper circuits. Here the minimum value is not set to 0, but this circuit clamps the waveform downward but not sets the limit to the 0. This was an example of a negative clipper. Now we will see how a positive clipper works. This circuit shifts the waveform downward and thus acts as a negative clamper. After discussing about the biased negative clampers, we will now design a biased positive clamper. In this circuit, as you can observe, only the position of this diode and this 5 volt supply is reversed. We will now switch on the circuit and observe what output we are getting. This is our input signal. As you can observe, 15 volts VRMS with 1 kHz of frequency, and this is our output signal. As it is visible that this circuit shifts the waveform upward and thus act as a positive clamper circuit, but the lowermost part of this waveform is not set at 0. Thus we can easily say that an external bias is present in the circuit. This was the working of a positive clamper circuit. That's all for this experiment. Thank you.